All right. We talked a lot about the parabolic conic sections and ellipses last week. Today you're just going to look at a couple applications with those parabolic conic sections to give you kind of a taste of what that's like. And then we're going to talk about radians and degrees today. So first of all, applications of parabolic conic sections. I wrote the equations on here just to kind of remind you. So remember, this is where we started with parabolas. Our vertex form, y is equal to ax minus h squared plus k. That's our nice little vertex form where h and k represented the vertex, right? And the only thing we changed with conic sections is we put 1 over 4p right here. This just helps us if we want to find the focus, right? Because the p represented how far away the focus was from the vertex. So we could find where that focus should be. And then we talked about, well, you can have parabolas, right, that go up. You can also have them that go down. And then if we switch the x and the y, so notice we switch those x and y's, right, we said they can go left or right. Now remember, when you switch the x and the y, the h and the k also switched. But again, this just allows us to have parabolas that open to the right and open to the left. Okay. Now applications, you really are putting the object or the image onto your own graph, so you can have it open whatever direction you want to. You just have to understand the information that you're finding based off of that. So we did a lot of applications like you see in these first couple pictures where we were looking at architecture, right, or the movement of an object over time. We did a lot like this related to distance and length and other things like that. When you're looking at the conic sections related to this, they're usually applications that have some sort of focal point in relation to signals that are coming in, or light is the example that we're going to look at a little bit today. Again, I'm just going to kind of read through these examples and show you these diagrams. If a parabola is rotated around its axis of symmetry, so that center point, if we were to rotate it, it creates like a bowl shape. You'll notice you see it here, right, in the back of this light. And you can see that if we were to cut that in half, it would create like a parabolic shape, okay? And this specifically is talking about, well, sometimes light originates at the focal point, so right here in the focus in the middle, and the light is being reflected by this parabolic shape and shooting it straight out into the rays that are actually symmetric to that axis of symmetry. So your light is shining straight forward. That would be something like the designing of searchlights or headlights, right? Light that's projecting and needs to project straight out. On the right, you have another example where some sort of signal or light is coming in. Now, this one specifically is talking about a telescope. So they're saying reflecting telescopes, right, magnify the light from the distant stars. So it's going to reflect the light that comes in, and it's going to reflect it right there to the focus. So now the light is coming in and using that parabolic structure to direct that incoming light. Same would be like a satellite that had a receiver there sitting at the focus. So the question is, where do we put that focus, right? Can it be over here and work the same? Can it be over here and work the same, right? It has to be right in that spot related to the focus. So let's look at an example. Here it says an engineer is designing a flashlight using a parabolic reflecting mirror and a light source. So you can see it there. The casting has a diameter of 4 inches. So notice down here, diameter of 4 inches all the way across, and a depth of 2 inches. So they've labeled that here already for us. It's asking us, well, what would the equation of this parabola used to shape the mirror be? So the first thing we want to make sure that we end up with in the end is an equation. And then it asks, at what point should the light source be placed? Okay, so we also want to figure out where should the light source go. Okay, and again, that's going to be related to the focus. So essentially, when we're doing an application, we're going to want to put it on a grid if we're going to build a function equation. And again, we could make this go any direction that we want. Probably the easiest to do is to sit it at the origin, except it's not going to go on forever, so I won't put an arrow on there. It's going to sit at the origin. That gives us a nice center of 0, 0. And we like vertical parabolas because we've practiced those the most. So we've got y is equal to, right, it's a vertical parabola. And essentially we've got that a x minus h squared plus k. Notice that this is sitting at the point 0, 0 here at the center. So essentially my h and my k there are going to be 0 and 0. If the diameter of the base of this reflective mirror is 4 inches, then notice this is going to be like out here at -2. This is at +2. And then it has a height of 2. So we can kind of make sense of our little parabola on there. Again, we like the center at 0, 0, because then our equation actually simplifies down to y equals a, and that's just x squared, because though h and k are both 0. So essentially we have most of our equation built right here. We just need to figure out the stretch or the shrink, that a value. And those of you that are really confident with just the graphs of them, you can probably look at it and say, well, 2 units away from the vertex should go up 4, because 2 squared is 4. But instead of going all the way up to 4, it's only going to 2, which is half that distance. So you would know that a is equal to 1/2. Again, we would say, okay, well then y is equal to 1/2 x squared. So essentially that's going to be my equation. Now, if you're not as comfortable with that, then you can just go off of any point. So if this is a point on my parabola and I have the point 2, 2, that's like an xy. And we said if we know an xy, that always works. We can plug it into this equation 2, right? We're solving for a, but we could plug in 2 for x and y, and then solve for a. So this would be like 2 is equal to 4a, divide by 4, and a is equal to 1/2. So then we would put that into the equation. Okay. Once we have our equation, now we want to find the light source. Again, the light source is just sitting at the focus. So remember, if this is our equation right here, the only difference between our original parabola equation and our conic section one was that a was always equal to the 1/4p. Okay, so if a is 1/2, essentially what we're saying is 1/2 is equal to 1/4p. And then we just solve for p. So here we cross multiply and we get 4p is equal to 2. Divide by 4, and notice that p is actually also 1/2. So what we're saying is that if we look over here in our diagram, that we should be putting our light source about a 1/2 inch above the vertex, right? If that's the distance to the focus. So that's what we would say there. Again, finding that focus, which would sit right there, we would say we need to place it 1/2 inch above the vertex. Okay, so you're going to practice a couple of those. Again, just interpreting what it's asking is the biggest part, and then using what you learned in determining the focus to help you find those parts.